Well, thank you so much for stopping by. It really means a lot to us from the Pattern and Practices team. My name is Jose Contreras, and I am the Principal Engineering Manager in this particular organization. We are tied to the all things that have to do with the Azure Architecture Center, and I'd love to, before I get going with my presentation, give you a little bit of a look into what it is that we do and how we do it. Okay, I cannot share that, that's all right. But let me tell you, basically, what my team does is, let's see, okay. My team is responsible for creating guidance that is engineering backed. And what that means is we actually go out and we talk to customers and partners like yourselves, and we try to identify what are the problems and the pain points that your customers are seeing today. But we are looking for problems and pain points at larger scale. Meaning, we like to take this with us, work with you, and figure out a generic solution that is compelling enough for not only yourself, but also other partners to bring into the data centers, into the production environments, right? Now, what I want to show you, what I want to talk about today is the outcome of an effort that we did in terms of researching how to process input streams using Azure Databricks. And by the way, all of this information and all of this, everything that you're seeing here will be made available to you, but at the same time, you can find us at at the Azure Architecture Center website, which the links will be provided in the end. But so let me tell you, what my team was aiming to do was to be able to understand how can we process two streams of data simultaneously and perform some what I would call some very light AI ML processing on it as these streams were coming in. If you guys are familiar with streams, basically this is a very basic architecture in the sense of you have two sources, right? And we're using event hubs for ingesting these different sources and aggregating them to the Azure Databricks processing pipeline, monitoring and storing Cosmos DB for later analysis via Power BI. A more detailed look into what the problem that we were trying to solve, and basically we were working with this customer and we identified that taxi company, they wanted to understand how can they correlate data coming from the ride itself in terms of geolocation, speed, traffic data points, and fare data, in order to understand how can they optimize their services and not only optimize their operations, but also deliver a more compelling experience to their customers, right? And basically, my team was in charge of analyzing the payload, taking a look at how this process worked, and creating what I would call a simulation of that payload so that we could actually replicate this in-house and understand how we can scale these operations over time. In order to do that, we created a generator, and we were able to leverage Event Hub, like I mentioned earlier, in order to create this and aggregate these streams. Now, one thing I want to also mention is, as part of the aggregation of the two streams in this reference architecture, is the fact that we were also aiming to enrich that particular data stream post-consumption. And one thing I just want to bring up, and one thing that was really important for us during the development process was to be able to identify what we call a partition key. And a partition key is a way for you to start distributing data within your cluster, right? Being able to allocate not only in storage, but also through the processing pipeline that we will have moving forward. Now, if you're familiar with Databricks or Spark, you know that all data that comes in, it gets turned into a job. And these jobs are processed within a single stage or multiple stages, right? And within these stages, there are multiple tasks churning on the job allocated to that particular stage. So I want you to keep that in mind, because what I want to showcase now was how we went through creating that pipeline, scaling that pipeline in multiple tiers in order to plan for capacity, but at the same time, being able to identify where we will find the bottlenecks in the design and in the assumptions that we had made. Now, one thing I want to showcase is that part of the monitoring that was available to us natively wasn't enough. And my team set out to build a monitoring library that you can include as part of your solution into the process, into this project, and you can actually be able to extract cluster and task-specific metrics that are natively to Spark that we previously didn't have. Right? So during the development of this solution or this reference architecture, we started to identify that we were experiencing certain, as you can see on the green lines, certain peak job latencies for particular processes that we were performing. And if you take a look at this, anything else that is not part of this 90% calculation task or set of tasks was not exhibiting any of these behaviors. So we were wondering, why is it that certain jobs within our infrastructure were suffering this latency? Now, remember when I mentioned that when you consume stream data, all these streams are turned into a job? This data is a job that then gets moved to a particular stage and then a particular task. What we previously saw was the job latency. Now, the first thing that we thought, hey, why don't we, now that we know what the job latency is, can we start digging in, like walking down the stack and understanding if the next stage is let's take a look at the staging latency and understand if there's anything else there that can start correlating and pointing us into the right direction. And clearly, sure enough, the correlation between the job and stage latency for this particular job type was easy to identify as problematic at this point. Now, having known this, we also wanted to understand what's our throughput throughout this process. And let me walk you through this. The green line is the amount of jobs complete. The blue line is the amount of jobs completed at the stage level, and the orange line is the ones completed at the task level. Remember, jobs first, stages, then tasks. And we could see the churn that we were having between the delta between the amount of throughput between the job and the stage compared to the task seemed a little bit disproportionate, right? And we wanted to understand at which point in time, why is this execution being so delayed? Now, you ask yourself, well, I have jobs, I have stages, but I also have a particular cluster that is actually processing all these jobs and distributing the processing within the stages, right? And we started to identify, okay, out of the multiple hosts that we have in our cluster, which ones do we feel, what's execution per host that we're measuring, right? And we started to understand not only this is the sum of the execution per minute per host. And we identified that we have two particular hosts, 6414 and 64.9, that are actually that have a performance degradation in them. Now, here's where we started to understand and maybe potentially pinpoint what could be the particular problem. When you started to break down the task per host or per executor running on this host, we started to notice that some of the hosts in our clusters, in the cluster, were not being utilized. As you can see, there's 0 tasks being processed at a particular point in time, especially here when we have more iteration or churn, right? We started noticing also that we have, semi-distributed amount of tasks on this stage per host on the cluster, 2, 4, 5, 6. But then, remember that the hosts that are giving us the most problem right now are, the green and the yellow host, both with 16 tasks allocated to them. To us, this allocation of tasks didn't seem reasonable. Something must be going on at this point. And we decided to start looking at metrics the task metrics per stage. Remember, once again, job, stages, tasks. We are at the bottom of the stack at this point. And we start to ask ourselves, within a particular task that is being processed in that stage, what's the breakdown of the compute that we're pursuing? And we would like to understand if there's any bottleneck that is not necessarily obvious to us. Now, one thing I want to showcase here, and it may not be as simple as to identify, but first thing that comes to mind is serialization and deserialization. Are we having an I/O problem here? And as you can see, our task deserialization time and result serialization times were negligible, right? 10 milliseconds, like almost 0 milliseconds for that. So great, we know that there is no I/O issue at this point. But let's take a look at the point. Let's take a look at the portion of that task that is actually computing the average that we're pursuing with this data, and is actually enriching this data at this particular point in time. That will be this executor compute time. And if you can take a look at this here, our execution time was actually just 1 second per task, right, at this particular point in time. Now, when you take a look at these numbers, the number that is it seems to be out of line here is this 3.7 seconds on the scheduler delay time. When you think about it, the scheduler delay time, what does that come to mind? The scheduler is the portion of the architecture that is in charge of distributing the jobs, or distributing jobs within stages and tasks. What does that mean? For this particular task and this particular host at this point in time, we are actually spending more time waiting for things to do. Let me say that again. We're waiting 3.7 seconds between things to do than actually the time it takes for us to compute or do that job. So with that in mind, we decided to understand, well, why are we spending so much time waiting for the next portion of the data that we need to process? Why are we doing this? And it came to us that the partition size of the data that we were processing was actually too small for that particular job. Meaning, data comes in, we were taking such a small portion of it and distributing that, and so that our partition key was just too small for this particular job. And the moment we started playing with that, or fine-tuning the partition size of the data that we were processing, we started to notice that we started to hit a sweet spot. And as you can see now, previously we had almost 3.7 seconds of processing for, a scheduler delay. We were actually waiting almost 4 seconds between tasks to pick, and by playing, fine-tuning that value, we were able to bring that down to 11 milliseconds and actually remain or keep a compute time of roughly almost 1 second, right? Now, I want to bring this. I love to bring this attention back to you, and it's the fact that let me go here. We noticed that the tasks that we're running within these stages in this host were struggling, and we started to identify that whenever a group of hosts are running slow, so the symptoms are that you're having high task stage or job latency and low cluster throughput. Now, one thing that we noticed was that this unbalanced execution and this is what we call partition skewing, the unbalanced execution of the data coming in through this stream was the root cause for this particular issue. Now, without us having been able to develop this additional library to be able to extract the Spark metrics from the cluster, from the task, from the executor, we could have not been able to identify what was going on behind the scenes. Right? Now, again, going back to the what could have caused this, and we believe truly that the data was showcasing that our partition count wasn't optimal. We were not shuffling the data properly at this scheduler level, so for us to identify this in a more efficient way. Now, another thing I want to showcase too is we were also able to take a look at the shuffle memory And look how interesting it is that most of the tasks that we were doing at a particular point in time may have been, the partition size may be really slow, very small, sorry, allowing us to process the throughput higher. And look how, for a particular host, how this, the size of the partition was way too large and consuming way too many resources than actually needed. So the key takeaways from that experiment, from this reference architecture is, whenever you are working with a data stream, you need to take into consideration a few things. Creating the proper partition key allows you not only to distribute the data to disk in the appropriate hashing partition or cluster, allowing you to maximize the use of your resources on the back end, but also at that processing tier or your middle tier, right? It allows you to, one, start to fan out these chunks of data into the jobs that you're performing, right? And at the same time, allows you optimizing that chunk size, whether it's too small or too large. And it's also, it's going to come down to a business need. You need to be able to identify, is my processing chunk too large or too small to be significant? And how is that supposed to affect the operations of my cluster? Now with that, I'd love to, these are the resources that we have online. Again, this all will be made available to you guys pretty soon. And I'm actually curious to understand how many of you, and just raise your hands, how many of you are actually currently using Databricks or are thinking about using it in the near future? So sorry, using it? Using it now? Okay, great. And if you have, please, like if there are any questions in regards to any pain points that you guys are seeing, any reference architectures, any sample workloads, anything in regards to your operations that you would like to come and discuss, please feel free to find me. Please feel free to connect on LinkedIn. I'm driving the charter of my team for the next year, and there's a few areas of investments that we're actually pursuing, and most of them revolve around IoT, streams, big data, AI, ML, and how Databricks and stream processing interacts with that entire pipeline. So please, we'd love to hear from you guys if you got any question after this, and thank you for stopping by. I appreciate it very much.